Okay, this video is more organizational than anything else. I might say a few conceptual words, but I'm trying to describing the next set of videos really. I want to connect this topic to wherever it appears in the list. We want to connect this topic to where I finished with measurement and measurement theory. It's going to be important in understanding both these two kinds of inference. So science is about making inferences. Science is about making observations, and from those observations, making inferences. Inferences in two different dimensions. Statistical inferences and causal inferences to date, on the videos at least, the only statistics we've seen have been descriptive of data that I had here on the chalkboard. Mean, median, mode, variance, standard deviation, so forth, related in discussion to data that actually fit on the board. We don't care about data that fit on the board in science. We care about data typically that we don't have. And statistical inference is different than the descriptive statistics that we've seen in the following way. We want to take small amounts of data, or relatively small amounts of data, and from those data make inferences about gigantic amounts of data, maybe all of the data, if possible. We want to take, for example, samples of American voters, samples of size 1,000, and from those 1,000 observations be able to say something about all American voters with some reliability or some confidence interval or credible interval. Language to come. Some people are shocked to hear at this stage, college, that there are differences of opinion between probabilists, between scientists, between the most sophisticated experts in the world. There are differences in opinion relative to what probability is. That's the sort of thinking you may be thinking, well, if scientists don't know what probability is, why am I taking this course? But such a position is short-sighted. It's extremely shortsighted. It would be like saying, after the release of the iPhone, which was the really first of the modern, really, really powerful smartphones. After its release, you realized very quickly that Apple is going to come up with a new model, probably by the end of the year, and the sort of humbug perspective, similar to the one I just described relative to understanding probability that it's not well understood by anyone, would be to sit back and say, well, I'm not buying an iPhone or any smartphone until they're finished improving them, until they've perfected it. And then you would have spent a good portion of your life without the power in your hand that so many of us have come to rely on all the time. So it is with statistics and probability. These are topics that are subject of current fierce debate and research, and topics that can generate arguments among extraordinarily bright individuals who study these topics. My view of it is it's like science in general. Probability is a work in progress to be understood. Our little sort of primer that we had on probability, those things are completely well understood, but theoretically, what probability is still a question in the minds of many, and a question certainly in my mind, or I would teach one of these or the other. There's actually two more alternatives that aren't even on the board. One of these or the other I would teach if I firmly believed that all the questions have been settled. There are two camps, two main camps. Maybe a third camp that will wind up subsuming all of these, but we'll leave that question to a more advanced course. This reads Bayesian and Frequentist. We'll spend some time here on Bayesian and Frequentist perspectives on statistical inference. Different perspectives on how it is that you take a small amount of data and say something with quantitatively defined sort of assurance, guarantees, hopes, promises. Take a small amount of something and say something about the larger group. Small number of units say something about. Frequentist versus the Bayesian perspective. My training, formally, decades ago, so it doesn't matter, was almost exclusively in the frequentist camp. Everybody really who went to school, where I went to school, graduate training at Ohio State, sort of inculcated into the frequentist tradition. And I ran into Bayes' rule, which is well, as we'll see, I'm not going to get deeply into this right here, ran into Bayes' rule while studying in the econ department at Ohio State, doing some methodology work in another department. But even then, it was in probably the mid-1990s before there was an explosion of interest in the Bayesian perspective of statistical inference, the frequentist, at least in teaching at the undergraduate level, and in many places even at the graduate level, the frequentist perspective, rightly or wrongly, correctly or incorrectly, is still the king. Certainly that's true in our department too. So most of my colleagues were trained in this tradition, and it's because of that I'm going to spend the most time there, and not because I'm evangelical about the frequentist perspective over the Bayesian perspective. In fact, that's not true at all. I'm not evangelical about either of these, or even some alternatives on understanding probability and statistical inference. I'm interested in those who are evangelical, very grateful to them for the material they put out that I consume. But I'm not sure as to which is the better. I think I can say I'm sure in some circumstances which is the better, but in general, I'm going to focus here. Not to the exclusion of this. In fact, one of the subsequent videos will be about this distinction. So I'm probably frustrating you, not defining Bayesian inference relative to frequentist inference. I'm introducing essentially the organizational part. Causal inference is different. So with statistical inference, you want to take small amounts of data and say something about large amounts of data. Maybe take a sample and say something about a population. In statistical inference. In causal inference, you want to say whether something caused something else or not. So you want to infer a causation and make reference to causality as a sort of on and off switch. This is either the cause of that or it's not. To say that it is to make a causal inference. And kind of similar, although these debates really aren't as loud in the literature sometimes as those between frequentists and Bayesians. There are different models of what it is that you need to do before you say one thing causes another in causal inference. I have two names up here, Reuben, R-U-B-I-N, and Campbell, C-A-M-P-B-E-L-L. Both gentlemen, their first names are Donald Reuben, Donald Campbell. And I have in parents, I have in quotation marks RCM, which is the abbreviation I'll use, referring to the Reuben causal model, and CCM refers to the Campbell causal model. Donald Campbell, now deceased, died in the 1990s. Donald Campbell was the older of the two. He was a psychologist at Northwestern, working at Northwestern. Can't remember where he trained. He spent his entire life really working on social science research methods and laid out a model for us to follow in the course of doing science. Science is all about causality. Theories are all about causality. Hypotheses, all about causality. And when and where and how and under what circumstances we can make an inference and say this causes that was really one of the driving forces of his entire career. Campbell, I'm going to spend more time here than here. That's not because there's a relationship between frequentists and Campbell that's native anyway. I think Campbell was a frequentist. And so the language of the Campbell causal model fits kind of nicely with the language of the frequentist perspective on statistical inference. But none of that is necessary. Nothing Campbell did precluded the idea that Bayesian work and Bayes theory is true. I'm going to do it again because most of the members of my department here are well versed in these traditions, and I sort of introduced the Bayesian alternative, I'm going to introduce the Reuben alter. Reuben is still a professor at Harvard University, rather than psychology. He is a statistician. It's interesting to me to follow these two. There are many things in common here. Many things in common here. And some distinctions that, again, can ignite some debates. The purpose of this set of videos is to give you a really thorough background on what's out there, and then I'll dig in here and dig in here on the two different inferential sides to give you sort of a package of tools that you can use in class and later on, maybe. So, where am I in this dimension? Frankly, I'm more interested right now in Reuben's method and Bayesian statistics, but I'm more interested in things other than that too. I wouldn't really categorize myself in any of these dimensions. I'm just going to explain what they have to offer, and again, dig in on two of them and hope for the best. So there's your introduction. The next one's going to be about Campbell's causal model.